Hey guys, in this video we want to talk about electrolytic cell calculations. And so the first two calculations that you've seen are almost exactly what you've done in galvanic cells. And so if I want to calculate the standard E cell, remember that standard gives that little knot symbol. You take your reduced value, subtract your oxidized value of the standard reduction potentials from the chart, and that will give you your standard E cell voltage. Remember, that's called cell potential. You can also find delta G, which is Gibbs free energy. And free energy is calculated by negative N. Remember, N stands for total moles of electrons transferred, which you can look at from your half reactions. F stands for Faraday's constant, which is a numerical value of 96,500, does not change. And E cell, that is your standard E cell, that is what you have gotten from up above. You can also do E cell at non-standard conditions. However, you don't normally see those type of calculations in electrolytic cells, just mainly the galvanic cells. Now, there's one additional equation that we have to talk about with electrolytic cells that will get you to be able to answer a whole bunch of different questions. So anytime they're asking how many coulombs, all right, coulomb stands for charge, that is Q, we'll talk about that in just a second. How long will it take? How many moles of electrons will it take? How many moles will I get? How many grams will I get? How many liters I get? You see how there is a plethora amount of questions that can be asked just by utilizing this equation. So this is probably the most asked thing whenever you are working with electrolytic cells. You can see it on both multiple choice and free response, so you're guaranteed to see it. All right, so let's talk about how to use this equation and what do we do. In order to answer these questions, we have to understand what this equation here is telling us. This is on your equation sheet, and the equation is I equals Q over T. So let's pick apart all the different parts of this. I stands for something that is called current. Current is where we're getting from our power source. So we're trying to figure out what is the current, what is the amount of charge per time that power source is giving us that's pushing through that reaction. Now, current is measured in amps. And so anytime you see the word amps in your problems, then that is the current that it is giving you. You can also measure current in coulombs per second. And so this is the technical units that we give current, which is coulombs per second. That means how much charge is going through for a certain period of time. This Q right here, this Q is going to be coulombs. This stands for charge. It is measured in coulombs, which is our big C, all right? And so that is our charge. It's how much charge is going through those wires. And then this little t that you see here, this stands for time. So this is where how I can ask how long does it take to plate out certain things. And so when I am measuring time, you see how this unit is in coulombs and this unit is in coulombs per second. What do you think our time unit must be in order for things to cancel out properly? Hope you got it. It is seconds. So I have to absolutely make sure that that time there is in seconds before I plug it in. Now, if you are trying to answer one of these questions, they'll have to give you some information. They could give you the time and the current. They could give you a gram amount. They could give you a liter amount. So we have to be able to work this equation in lots of different ways. So we're not only just dealing with this equation, we have to be able to tie it into dimensional analysis as well. And that's how you answer some of these questions. How many moles of electrons, how many moles, how many grams, how many liters. So we can take this equation and solve for Q, which is our coulombs, our charge. And we can take our coulombs and do dimensional analysis to transfer it into moles of electrons. Now, how we convert that is by using our conversion factor of Faraday's constant that we get from F in delta G equals negative N phi. Because that Faraday's constant says there's 96,500 coulombs for every 1 mole of electron. So we can put this in dimensional analysis to convert to moles of electrons. And that would answer this question here. How many moles of electrons could I get? Then I could also convert to just regular moles. Now, how I convert in dimensional analysis is I have to look at my half reaction ratio. So for instance, if I look at this half reaction here, there is 1 mole of Ag for every 1 mole of electron. For this half reaction here, there is 1 mole of O2 for every 4 moles of electrons. So we're using a conversion factor within our half reactions for that. Now, if I know what regular moles are, then I can answer my question, how many grams? So I would just convert to grams using molar mass. Or I could even convert to liters. If I was at STP, I would convert to liters using 22.4. They will never give that to you though. So instead, remember, if you're not at STP, if you're instead at standard conditions, which is 298 Kelvin, that's what this means, standard conditions, then you will have to use PV equals nRT to figure out your volume instead of the 22.4. So I know that this is kind of like throwing a lot at you. Why do we use this equation? What scenarios are involved? Well, we can do something called electroplating. And what that is like when we get certain jewelry, when we get our coins and things like pennies and nickels and all of that, all of those things are electroplated. When you have like a gold ring or something like that, it's not 100% gold. What they do is they take a cheaper metal and then they plate gold on top of it. And how much you get is relative to the price. And so same thing with coins. The coins are shaped out with a very cheap metal, and then your copper, for instance, for a penny, is plated on top of it. All right, so most of the jewelry and precious gold, precious metal things that we have are all electroplated on top of a cheaper metal. And so this is where that's coming from, all of these calculations. All right, so I want to go through an example problem with you dealing with silver nitrate, and we'll talk about all of these different things. And so first of all, silver nitrate, I have to analyze it just like we did in our conceptual video to figure out who's going to be oxidized and reduced, what is actually happening there. So the very first thing I do is I look at my solution and I notice that this solution is aqueous. So we have to apply those rules. Remember, the rules say my cation is reduced unless it's a group 1 or 2. My anion is oxidized unless it's a polyatomic ion. So what I see here is my cation that is not a group 1 or group 2. So therefore, Ag is going to be the species reduced. And what I have here is my reduced half reaction written here. Now, again, you don't have to memorize these half reactions or these cell potential values. You do need to be able to kind of write them out, but most of the time they will be given to you in the problem as like a little data table. So Ag is reduced, it is reduced at the cathode, and we have our half reaction with our standard E cell value for it. Now, because nitrate is a polyatomic ion, it will not be oxidized. Water will be oxidized instead. So instead, water will be oxidized. Silver was the one that was reduced. And so when water is oxidized, remember that it produces oxygen gas there. And so we have our half reaction for water being oxidized, which is 2H2O yields O2 plus 4H plus 4 electrons. And that's equal to 1.23 volts. And I got that from our standard reduction potential chart. Let's just practice, just because, writing our overall reaction for this entire scenario. And so remember, what we do is we look at our oxidized and reduced half reactions and we kind of combine them. But before we can combine them, we have to make sure that our electrons are balanced and canceled out. And so do you see how I have 1 electron on this side of the yield sign? I have 4 electrons on the opposite side. In order to balance that out, I'm going to have to put a 4 right here and distribute it through. So there's going to be 4 Ag pluses, 4 electrons, and 4 Ags. Now I get to bring everything down because I have balanced out those electrons. So we have 4 Ag plus 2 H2Os yields O2 plus 4H plus 4 Ag. So this is my total net ionic equation for the entire reaction that is occurring there. All right. So this is just the conceptual part. Now let's get into the math. All right. We want to calculate our standard E cell. So we take our reduced value and we subtract our oxidized value. Now notice how I changed some things around here. That does not change these E cell values here, okay? I don't alter those in any way. So I'm going to take my reduced value, which is 0.8, and I'm going to subtract my oxidized value, which is 1.23. And now I'm just going to complete the math there. So 0.8 minus 1.23 is equal to our standard E cell, negative 0.43 volts. So this is the answer to my standard E cell. Notice how my E cell here is a negative quantity. That's true for all electrolytic cells. Now let's calculate our delta G. So we've got to plug in our different values. So negative value N stands for moles of electrons totally transferred. And so remember, that is our balanced number here. So we have 4, because 4 electrons is going from the oxidized to the reduced species. So I'm going to plug in 4 moles of electrons. I'm going to plug in Faraday's constant, which is 96,500 coulombs for every mole of electron. And then I'm going to calculate or plug in my standard E cell, so negative 0.43. Remember what a volt is equal to? It's equal to a joule per coulomb. So now let's cancel out our units. Moles of electrons are gone, coulombs is gone, and I'm left with just joules. So when I take my negative 4 times 96,500 times negative 0.43, I end up getting this number here, positive 1.66 times 10 to the 5th joules per mole reaction. Remember, we include the per mole reaction because that is one time that the reaction goes through. That's how much energy we get. And notice that this is a positive quantity. All electrolytic cells have positive delta G values. Now, is this my final answer? You see how I bubbled it in. It is actually not my final answer because we don't want our delta G quantities to be in joules because they're so large. We instead want to convert that to kilojoules. So I'm going to erase my little circle here. I'm going to divide by 1,000 to convert to kilojoules. So if I take this and divide by 1,000, I get positive, so delta G at standard conditions is equal to positive 165.98 kilojoules per mole reaction. And this is my final answer. This delta G being positive tells me that my reaction is thermodynamically unfavorable, which means this reaction would not happen unless there was an external power source applied to it. That external power source that's hooked up to it, whether it's a battery or whatnot, is making this reaction happen because it is thermodynamically unfavorable, okay? All right, so that takes care of this stuff. Hopefully that's kind of just like review because you've done it with your galvanic cells so much. Now we want to talk about this new concept here. And so how many coulombs, how long, all of that stuff. How do we do these calculations here? So I'm going to give you a couple of scenarios dealing with that. I'm going to erase all of this that I've written so far so I have enough space to work. So give me 1 second. Okay. Now, if you have the question, how many coulombs are involved, you have to be given like a couple of different things as far as information. If I want to know how many coulombs I have, then I have to know either my current or my time, or and that's about it. Or you could actually work backwards from grams or something to find coulombs just with dimensional analysis. So there's lots of different scenarios that I have here. If I want to know how long, then I could have to have my charge or my current to solve for time, or you can have your current and work backwards in dimensional analysis to find coulombs and plug it in here. If I want to know how many moles of electrons, I could either work backwards from grams to here, or I can work forward by having my current and my time given, find coulombs, and then go to moles of electrons. So you see the trend. There has to be some information given to you in order to be able to answer the questions. And so let me give you a scenario here. Let's say that we have a current of 5 amps. Remember, amps is the same thing as coulombs per second. And I let that run for 100 seconds. So here I am given current, which is I, and I am given time, which is T. Let's ask ourselves a couple of different questions. The first question I want to know is how many moles of silver will I get if I let this scenario run for a current of 5 amps for 100 seconds? How many moles of silver can I get out of there? What I'm going to do is first plug in this I and this T in order to find coulombs. So that's my first approach. Now, I have to double check and make sure that this is in coulombs per second and this is in seconds. If your time is not in seconds, you will have to convert it to seconds before you can plug it in. So rearranging this formula, does it make sense that Q, which is our charge, is equal to I times T, our current times our time. We're cross multiplying here. I times T is equal to Q. So we plug in our I, which is 5 coulombs per second. We plug in our time, which is 100 seconds. And do you see how our seconds end up canceling out as far as a unit go? So we give Q equals to 500 coulombs. Now that we know coulombs, I then can go into my dimensional analysis. And I have to go from coulombs to moles of electrons first. So we start with coulombs, we get into moles of electrons. How we do that is we use the conversion factor, 96,500 coulombs. Since coulombs is top, I want to put that on the bottom. Coulombs will be able to cancel out, is equal to 1 mole of electron. So that is equal to 1 mole of electron. And notice how my coulombs cancel out there. Well, that doesn't quite answer my question yet. This would answer if I were to stop here, how many moles of electrons that I have. But I can go one step further to convert it to just moles. So how I convert moles of electrons to just regular moles is by using the half reaction that I originally started with. So originally, before I put this in here, there was 1 mole of electron for every 1 Ag, right? This right here was my original half reaction. 1 mole of electron, I want to put that on the bottom, is equal to 1 mole of Ag. And so that cancels out my units of moles of electrons. Well, now to do my calculation to get moles, and that will be my final answer because that's what I'm trying to find, I'm going to take 500 divided by 96,500, and that gives me 0.0052 moles of Ag that is produced. Now, what if they asked how many grams? Well, if I know moles, I can get into grams easily. That's back in stoichiometry, right? If they asked how many liters, then I could do that pretty easily as well, because I would just take these moles and plug it into PV equals nRT to be able to find that. Now, I would have to be given some extra information like a pressure reading and a temperature reading. But if we're at standard conditions, we do know that pressure reading, which is 1 atm, and we do know that temperature reading, which is 298 Kelvin. So we could be able to plug in our information into PivNert to figure out how many liters we have. So this is how we kind of work by given the amps and the time. I want to show you how to work backwards now. How can we go from maybe given a mass of silver and work backwards to find maybe like a current or something like that? So let's go through a scenario involving that. Let's say in this scenario, what we are given is a time. So let's use 20 minutes is our time. And let's say that we want to plate out 2.3 grams of silver. And my question is, what is the current? So let's add a thing here. What will the current need to be at? All right, so I have 20 minutes, that's my time. I have 2.3 grams, that is my gram amount, and I want to figure out what current do I need to set that out to get me the 2.3 grams of silver. And so what we have to do is work backwards. Instead of using this initially, we want to start with the dimensional analysis to find coulombs. Once we find coulombs, we can plug that in, plug our time in, and we'll get our current. So that's our game plan, that's our approach. So I'm going to start with 2.3 grams of silver. So if I want to work backwards, my very first thing I want to get into is moles. So just like before, silver I think is 107. Silver 107.87. We're just going to call that 108. So 108 grams of silver is equal to 1 mole. You see how this is just stoichiometry, right? Now, I've gotten into moles. I have to work backwards to get into moles of electrons. So what conversion factor do I use there? Remember, I use my half reaction ratio. So we use our original half reaction. 1 mole of silver. Do you see how I'm able to cross out these units here? Is equal to 1 mole of electron. Now I got this from this half reaction. So moles of silver is gone. Now I want to convert back to coulombs. And so to go from moles of electrons to coulombs, we use this conversion factor. 1 mole of electron is equal to 96,500 coulombs. And you see how our moles of electrons is gone, and I'm left with just coulombs. So I'm going to stop my dimensional analysis here, and I'm going to solve for coulombs. 2.3 divided by 108 times 96,500. That gives me 2,055.1 coulombs. This does not answer our question because this just tells us our charge. What we're trying to solve for is our current. So we are going to have to plug in our charge, this coulombs. we're going to have to plug in our time, but I noticed something's missing here. We have our time in minutes. Our time needs to be in seconds. So we're going to do a little conversion here. 20 minutes to seconds. So there is 1 minute equal to 60 seconds. So you see how we've got minutes gone. We've got to convert that to seconds. So 20 times 60, I don't know why I'm plugging that in my calculator, but is equal to 1200 seconds. So to solve for current, amps, coulombs per second, I'm going to take my coulombs, which is what I found from dimensional analysis, and I'm going to divide by my time given to me in seconds. So 1200 seconds. So let's do this calculation. 2055.1 divided by 1200 gives me 1.71 coulombs per second, or we can use the term amps for our final answer. And so this is how you work your coulombs, your current, your time calculations. You can answer a whole bunch of different questions. You can work backwards to here, and you can work forwards to here. So I hope that is helpful. I hope it makes sense to you guys, and we are going to be doing lots of practice problems with this. So let me know if you have any questions.